My name is Don MacPherson. I'm Technical Director with Hydrocomp. My purpose here today is to give you an overview of the speed and power module that we have developed for Orca3D. And I'd like to start a little bit with a brief description of what the module is and, almost as important, what it is not, just to give an appropriate scope for the features and capabilities. It is bare hull resistance prediction. There is no explicit appendage or shallow water or sea state drag. The reason that, one of the reasons that we focus on the bare hull drag, of course, is that Orca3D is a hull design tool. So as part of the design cycle, the bare hull resistance, of course, is the principal drag component of any vehicle. So understanding the total bare hull drag is very important, of course. It gives you a power estimate. It also provides design guidance, and we'll have an opportunity to speak about that in a little more detail and also see an example of that. The design guidance side, again, focuses back on the bare hull resistance prediction, where the intent is to provide suggestions and the sensitivity of changes into principal hull parameters. And then finally, it provides some data export to more comprehensive resistance and propulsion tools if you want to take this data and extend your analysis into something more detailed and thorough. And it is not propulsion analysis. There's no propeller sizing. There's no explicit propeller propulsor analyses of any kind in this module. Just a very quick background of the development history of the module that we have prepared for Orca3D. Hydrocomp has been a corporation since 1984, and we have focused exclusively on applied hydrodynamics in that entire time. We specialize in hull form hydrodynamics, resistance and propulsion prediction, and also we do a lot of propulsor work, notably propeller design. The module is derived from the code that was originally developed for our NavCAD software, which many of you have heard of, I'm sure. And I know that some of you are running NavCAD right now. NavCAD provides very comprehensive resistance, propulsion, and duty analyses, and it's from the resistance parts of NavCAD that we have extracted the features that we've incorporated into Orca3D. So it's built from a very stable, very mature, very long-standing code library. And in fact, one thing that I will say here, there's actually some features in the Orca3D library that are a little more advanced than you find in NavCAD. We'll be seeing some of those things in migrate over to our future NavCAD development, but you actually have an opportunity to run those first here in Orca3D. So let's get into the bare hull resistance prediction. When we are discussing bare hull resistance, there are two principal styles or methodologies of resistance, the first being planing and the other being what we would refer to in the hydrodynamic community as CT-based, but for our purposes here, we'll call those displacement and semi-displacement. Let's talk about the first one here for a moment, the planing analysis. This is the Savitsky general case that we're using, which is an equilibrium trim analysis. Those of you who may be familiar with Savitsky may recognize that there are two different approaches. There's what's called the simple case, and then there's what's called the general case. The simple case puts all of the forces and moments through the center of gravity. The general case incorporates lift and drag or thrust vectors from different components, and that's the methodology that we have employed here. it's an equilibrium trim analysis whereby the lift and drag on the planing surface, as well as the thrust vector of the propeller shaft line, are incorporated into determining this final equilibrium trim solution. And it's at that trim that the analysis resolves itself and gives a total bare hull resistance. Now, one of the characteristics of the Savitsky methodology is that it was based on what was called a prismatic planing surface. And the easiest way to think about that is just a simple wedge. It is a wedge-type shape that was towed in a tank at different angles of trim, and the different lift and drag components were measured and recorded and resolved into underlying equations. Now, one of the weaknesses of the conventional Savitsky method has always been that the hulls that we actually design, as can be seen by this simple graphic here, are not truly prismatic. They have curvature in all directions. They have pad keels, they have chine flats, they have strakes, they have variable angles of dead rise. There's a number of different things that make a real hull different from the original Savitsky tested model. So what we've done for Orca3D is that we have developed a calculation, internal calculation, that comes up with effective dead rise at various station locations and an effective chining beam, or a chine width of the section, and determined a comparable dead rise and chine beam that's appropriate for the Savitsky methodology. So it can handle a widely variable planing surface very, very effectively. Now, there was an extension to Savitsky's original data, which he published in 1964 by Savitsky and Brown, that incorporated a trim correction both for resistance and the final trim solution for what was called a warped surface. They implemented it as a chine angle against a horizontal baseline, and so we've incorporated that in this method as well. Let's proceed to the other method. The Waltrip analysis. Now, this is for displacement and semi-displacement hulls. I made mention earlier to what was called a CT-based calculation. Unlike the Savitsky, which is a solution of forces and moments, a CT-based is the traditional Froude scaling approach, where you have residuary resistance, C sub R, plus frictional resistance, C sub F, equals total resistance, C sub T, in coefficient form. That's the CT-based. And the Waltrip is an extremely popular version or prediction method that employs this CT-based methodology. Now, there are many, many different publications and implementations of Waltrip and Menon that are in various publications. Principles of Naval Architecture has one. We employ a 1988 variant that was published by Marin in an obscure little Eastern European conference. And what we have also done is, because of the work that we have and the number of users that have provided feedback to us and our own validation studies, there are a number of constraints and corrections that we have applied to the traditional Waltrip algorithms to make them more well-behaved and to ensure and improve accuracy, more appropriately to ensure that the scope of the data is used appropriately. The Waltrip analysis that is implemented in Orca also is able to take the hull form geometry and determine certain bow and stern details that are very important for a reliable resistance prediction. In the bow, it calculates half angle of entrance, and in the stern, it calculates the immersed transom area. But also, there are characteristics of the stern that are quantitatively described in the Waltrip method as a stern coefficient. And what we have done is we have developed a very rigorous quantitative way of taking the stern geometry and identifying what an appropriate stern coefficient is. So it's a very reliable, very easy way of getting the data that you need out of your Orca3D model and into your Waltrip analysis. Now, the third feature of the Orca3D analysis is a design guidance that I had mentioned earlier. This is really a sensitivity analysis. It provides a summary of the effect of changes in hull parameters. And I want to stress this is not optimization. Anybody who knows me knows that I have a particular problem with the concept of design optimization, not in theory, but in how it's frequently implemented. Optimizations can be very flat curves. So what we do with this is we give you the sensitivity in the planning analysis of what a change in beam, change in dead rise, LCG, or shaft angle might be. We also give you a ranking as to how important each change will be. In the Waltrip analysis, we use a different set of parameters that are germane to a CT-based style of calculation: maximum section coefficient or midship coefficient, water plane area coefficient, the immersed transom area, and the longitudinal center of buoyancy. So we'll get an opportunity to see how these are employed. Let's begin a first example for a planing analysis. 20-foot center console hull, you can see the graphic there. We'll select the planing surface on one side only, include the chines and the strakes in that because our calculation is able to use those to determine an effective dead rise for the planing area, and we will also include the shaft line. So let me switch over to the planing analysis, and so bear with me for just a moment here. I need to clean up my screen. Okay, we have our hull. You can see the perspective view. I'm going to maximize that just a little bit. What we're going to do is do the speed and power planing analysis. Now, prior to that, you can define the design condition in order to have the data automatically entered for you. I've already done that in the interest of saving a little time. But we will go right to the planing analysis. It's asking for the planing surface. That's not the one I want. Sorry about that. That's the one I want. Now I've chosen the starboard side. We want 1/2 of the hull form. I'm bringing in the data from the design condition. Now we'll see that no vertical center of gravity is defined on this, and we're going to enter that 1.5. My center of gravity, you can see, I'm sorry, my baseline for the calculations is at the water plane. So I'm going to be putting my center of gravity 1.5 meters above the water plane, fairly high. Now I'm going to identify the location of my thrust line vector with these three fields right here: the propeller, longitudinal, and vertical centers of effort, and the shaft angle. So I'm going to place at the end. I'm going to place also at the end. Now I have my LCE, longitudinal center of effort, vertical center of effort located, and my shaft angle I'm going to pick up from just 2 points on the shaft line. You can see it's 10 degrees. I'm going to run this from 5 to 45 knots at a 5-knot increment. Set my design speed at 40 knots. Now my resistance design margin, this is to provide some measure of accommodation for things like appendages, added windage drag. I'm going to add a fairly sizable figure at 20%. Appendage drag of planing hulls is traditionally significantly higher than for displacement and semi-displacement hulls. So it can run, depending on the application, as high as 30%. 20% is a reasonable figure. And contemporary propulsive efficiency varies depending on the propulsor, but I'm going to use a typically average value of 60%. I will calculate my results, and we should see a warning here that just simply mentions that the surface that we have chosen has some discontinuity in it. These various strakes and the chine flat. We do indeed want to incorporate those, so we will say yes. The analysis runs the calculation, and we should receive the resistance report here momentarily. We can see a recreation of our data at the top, a summary of our principal parameter checks. Everything looks fine. These are minimum and maximum ranges for these principal parameters for the Savitsky prediction method. Here's results, speed range with our bare hull drag, our total drag, effective power in horsepower, and by taking our total effective power and dividing by our propulsive coefficient, we get a prediction of our total engine power. Now I'd like you to look at this second page where we see some of the detail parameters. We have a calculation of the effective planing beam and the effective dead rise. Now you'll see that the values of the effective dead rise was very, very constant. And if you look at the stern of the hull, that makes sense. We have very little change in the angle of dead rise here. If you had a significantly variable surface, you'll see the effective angle of dead rise change. This is a resistance over weight ratio, a porpoising check. Now there are three options of output that you can get here. It will either say OK check or fail. There are three different porpoising criteria that are used in the analysis. If all of them say OK, it comes back OK. If all of them say fail, it comes back fail. If any one of them says fail and the other two are OK, it will say check. The prediction check looks at further calculation and analytical checks having to do with wetted keel length and Froude number, for example. So each speed gets its own check. Now this is the sensitivity analysis. This is the design guidance. What this tells you is that of these four principal hull parameters, effective planing beam, effective dead rise, longitudinal center of gravity, and shaft angle, to reduce drag, we will want to reduce all three. But let's look at the sensitivity. The larger the number, the more significant the change is going to be. Shaft angle makes very little difference. However, moving the longitudinal center of gravity makes the most difference, strictly from a drag standpoint. So this gives you some potential design guidance if you want to find ways to improve the performance of your hull. I'm going to close this right here. The last thing that I want to mention is when you're satisfied with your design in the Orca analysis, you can export the data to either Swiftcraft or NavCAD from this form right here. I'm going to close this form right now, and I will pop back over to my PowerPoint, briefly give an overview of the next example, which will be the Waltrip analysis. This was for a 180-foot offshore supply vessel that we had in our library. We'll select the surface. That's the principal buoyant volume. We could talk about that afterwards a little bit, but we do not want to add volumes necessarily for appendages, skegs, things like that. We will add that into the margin itself. So let's go to the Waltrip analysis here, and we'll do very much the same thing. Speed, power, Waltrip. Select the surface that we want. In the analysis of this surface, the displacement, LCB, for example, those came from the design condition stability analysis. Transom area, the area of any bulb, the center of the bulb, the half angle of entrance and the stern coefficient, that was from a more detailed analysis through the library. We'll do a minimum speed of 2, a maximum speed of 16, speed increment of 2 knots, and set the design at 14. I'll do a 10% margin here, and I'll also set my propulsive efficiency at 60%. Run our calculation. See the results, recreation of the data, initial parameter checks to make sure that the scope of our hull is within the range, and in all cases it is within the range. Here's our speed, our coefficients, resistance bare hull, resistance total, effective power total. Second page, again, individual speed prediction checks, total propulsive power, and here's where we see our sensitivity analysis. And what we find is that immersing the transom area, we actually want to get a little bit more, but it's fairly insignificant. But the water plane area is tremendously significant. This was a very full hull, as you can see. It's a very full, very shallow hull. It had a large half angle of entrance, about 38 degrees. If it's possible to reduce the water plane area, you can then reduce a number of the components that would affect wave-making drag, for example. So this gives you some guidance that can improve your hull. And again, on the following pages here, you'll get plots of the results themselves. So I will close out that. Again, you can export to Swiftcraft or NavCAD if you would like.